I've spent years running proxy farms for real scraping operations, and the question I get asked more than any other is SOCKS5 or HTTP. Which one should I use? People ask it like it's a stealth decision. Like flipping a switch from HTTP to SOCKS5 is going to be the thing that keeps their scraper off a block list. It isn't. I want to walk through why. Because the honest answer surprises most people, and because the wrong assumption here has cost me actual debugging hours on farm operations more than once. Faninin sent to that seat, so let's start with what people are really asking. When someone asks me SOCKS5 or HTTP, what they actually mean is which one gets me fewer blocks. That's the real question hiding under the surface. And the honest answer is that the proxy protocol has almost nothing to do with your block rate. What gets you blocked is IP reputation, request pattern, and the fingerprint of the client making the request. SOCKS5 versus HTTP is a plumbing decision, not a stealth decision. But here's the twist. The plumbing still matters, just not for the reason people think. Pick the wrong one and you get silent failures that look exactly like blocking but aren't. And that distinction is worth understanding properly before you touch a single line of proxy config. Let's talk about what an HTTP proxy actually does under the hood. An HTTP proxy is built to understand HTTP traffic specifically. When your scraper sends a request through it, the proxy reads the HTTP headers, it knows what a GET or a POST looks like, and it can inspect and sometimes rewrite parts of that request before forwarding it along. For plain HTTP traffic, the proxy sees the whole request, nothing hidden. For HTTPS, which is most of what you're scraping in 2026, most HTTP proxies operate in what's called connect mode. Your client sends a connect request, the proxy opens a raw TCP tunnel straight to the destination, and everything after that point is encrypted end-to-end. The proxy literally cannot read your HTTPS payload once that tunnel is up. But conceptually, it's still operating at the application layer, and it only speaks HTTP-shaped traffic, which is a distinction that matters in a minute. Here's why that matters for scraping specifically. Almost every scraping tool you'll touch defaults to HTTP proxy support out of the box. Requests, URL-free, Scrapy, Playwright, Puppeteer, Curl, all of them treat HTTP proxies as the first-class citizen. Configuration is a single environment variable or a one-line proxy dict in your code. Support is deep. It's well-tested because HTTP proxying is the most common use case on the entire internet, not just in scraping. So if you're new to this and you just want something that works without fighting your own tooling, HTTP is the path of least resistance, full stop. Now let's flip to SOCKS5, because this is where people start getting confused about what it actually buys them. SOCKS5 operates lower down the stack at the transport layer instead of the application layer. It doesn't know or care whether you're sending HTTP, a raw TCP socket, or a UDP packet for something like a game server. It just relays bytes to a destination IP and port and gets out of the way. That makes it protocol agnostic in a way HTTP proxies simply aren't built to be. You can push non-HTTP traffic through a SOCKS5 proxy and it won't get confused by what it's looking at, because it isn't looking. For scraping specifically, there are a small number of concrete cases where that agnosticism actually matters. Say you're pulling data over a raw TCP connection that isn't standard HTTP or HTTPS, that happens occasionally with certain AP integrations that don't ride on top of HTTP. Or say you want one single proxy that a full browser automation stack can route everything through, including WebSocket connections, without needing protocol-specific handling for each traffic type. SOCKS5 handles WebSocket upgrades cleanly precisely because it never inspects the payload in the first place. Or you're chaining a proxy through something like Tor or an SSH tunnel, and both of those speak SOCKS natively, so SOCKS5 slots in without translation. Beyond that, SOCKS5 also supports UDP associate, username and password authentication, and IPv6 destinations more consistently than most HTTP proxy implementations manage. Now here's where I want to slow down, because this is the part I've actually lived through on farm operations, and it's cost real time more than once. Picture a scraper built on a library that defaults to HTTP proxy handling. Someone points it at a SOCKS5 endpoint instead, maybe because a provider only offered SOCKS5, or because someone copied the config from the wrong place. And instead of getting a clean, obvious connection error that tells you exactly what's wrong, you get partial failures. Some requests go through fine, others just hang. Tele-S handshakes fail intermittently for no visible reason. The proxy silently drops packets it doesn't know how to route because the client is speaking the wrong dialect to it. And the failure doesn't announce itself as wrong proxy type. It doesn't give you a clean error message pointing at the actual problem. It looks like the proxy is bad, or it looks like you're getting rate limited by the target site and people chase the wrong problem for hours. I've watched this exact scenario burn an afternoon before. Someone convinced their proxy pool had gone bad, swapping providers, burning credits, when the actual issue was a client library that never had proper SOCKS5 support configured in the first place. The fix is almost always boring once you find it, which is exactly why it's worth checking first before you blame the proxy itself. Check the client library's proxy support before you touch anything else. Python's requests library, for example, needs the PySocks extra installed, and it needs a SOCKS5H scheme in the URL, not just SOCKS5, if you want DNS resolution to actually happen through the proxy, instead of resolving locally on your own machine. That local DNS resolution piece matters a lot, because it can leak your real network path even when the connection itself is properly tunneled through the proxy. Node-based tools have similar gaps depending on which HTTP agent they're using underneath. None of this is a proxy quality problem. It's a compatibility problem. And honestly, it's the single most common reason a working proxy list suddenly looks broken right after some unrelated code change. Let's talk performance for a second, because there's a lot of folklore floating around here, and not much of it holds up under actual testing. HTTP proxies running in connect mode and SOCKS5 proxies both end up doing roughly the same job once HTTPS is involved. They open a TCP tunnel and then get out of the way. Once that tunnel is established, there's no meaningful throughput difference between the two protocols for a single connection. The overhead lives in the handshake, not in the ongoing data path. So once you're moving bytes, the protocol choice basically stops mattering. Where you do see divergence is in connection reuse and pooling behavior, but that depends far more on the specific proxy server software than on the protocol itself. Some HTTP proxy implementations are genuinely better at keeping persistent connections alive across multiple requests, which cuts down the TCP and TLS handshake cost you pay per request. Some SOCKS5 implementations handle a lot of concurrent connections through the same proxy process more gracefully under heavy load. But neither of those is a fixed rule baked into the protocol. It's a property of the specific software and how a given provider has configured it. So if you ever see a claim like SOCKS5 is faster floating around without a specific setup backing it up, that claim isn't worth trusting on its own. Now here's the part that actually matters. If what you care about is whether your scraper gets blocked and it has genuinely nothing to do with SOCKS5 versus HTTP. A detection system on the receiving end is looking at things like your TLS fingerprint, the JAR3 or JAR4 hash of your handshake, HTTP header order and casing, TCP window sizing, request timing and cadence, and behavioral signals like mouse movement inside a headless browser session. Whether the IP that eventually hit their server came through a SOCKS5 tunnel or an HTTP connect tunnel is completely invisible from their side of the connection. Both protocols end up producing the exact same raw TCP connection landing on the target server. So if you ever read a proxy comparison piece claiming SOCKS5 is more anonymous or harder to detect, what's actually happening is that the article is conflating protocol choice with everything else that goes into a request. What actually drives detection outcomes is the IP type. Residential and mobile IPs carry very different reputation than data center ranges do. How many requests are coming from that one IP inside a given time window? Whether the client's TLS and header fingerprint actually matches what a real browser would send, and whether the site owner's terms of service and robots.txt even permit the kind of access you're attempting in the first place. None of that, not one piece of it, is decided by which relay protocol happens to be carrying the bytes underneath. Authentication and rotation work basically the same way across both protocols too. Both support username and password authentication, and both get used by rotating proxy providers to hand the scraper a fresh exit IP per request or per session. That rotation logic lives entirely on the provider's gateway, not inside the protocol itself. A provider running a SOCKS5 gateway and a provider running an HTTP gateway can implement the exact same rotation policy, the same sticky sessions, the same pool size behind either protocol label. So when you're actually comparing providers, ask directly about rotation policy, pool size, and IP type mix. The protocol name sitting in the connection string is not going to tell you any of that on its own. So here's the practical way I'd actually decide, and it's the same advice I give anyone running scrapers at any scale. Use HTTP proxies as your default. Client library support is broader. Debugging tools understand HTTP proxy errors far better, and most scraping frameworks assume it without you having to configure anything extra. Reach for SOCKS5 specifically when your stack needs to tunnel non-HTTP traffic. When you're layering the proxy through something that already speaks SOCKS natively, like an SSH tunnel, or when a specific provider only offers SOCKS5 endpoints and you genuinely have no reason to avoid it. And before you switch, confirm your library actually supports SOCKS5 properly, including DNS through proxy resolution, so a protocol mismatch doesn't get misread as a block when it's really just a wiring problem. Whichever protocol you land on, keep this in mind. The proxy is one single layer of a request. It changes your exit IP, and depending on setup, it changes your DNS resolution path too. That's genuinely useful. But it does not change your TLS fingerprint. It does not change your header order. It does not change your timing pattern. And it absolutely does not change whether the target site permits automated access to the data you're after in the first place. Scraping cleanly at any real scale means treating the whole request as one system, not assuming a protocol swap is going to solve a detection problem it was never designed to solve. I run the proxies behind real scrapers myself. The full written guides and the proxy setups I actually use are at proxyscraping.org, including a deeper breakdown on residential versus mobile versus data center IPs, and how rotation policy actually affects block rates in practice if you want to go further than what I covered here. Full written guides and tested proxy picks at proxyscraping.org, and if this was useful, go ahead and subscribe.